So welcome back to our study of Newton's laws. This chapter is an application of Newton's laws. So it's actually obviously a continuation of chapter 5, where we'll continue to solve problems focused on Newton's laws. And in addition to that, though, we'll also learn about some new forces, particularly the force of friction. That's going to be the main focus in this chapter. And then we'll also continue using our kinematics equations as well as the trigonometry equations. So if you look at this picture here, we can actually find our right triangles. Here's the one on this side and the one over here. So we'll continue to look for right triangles in our sketches or drawings. And we'll continue applying Newton's laws in addition to learning about friction being the main focus, but also tension too. In this picture here, we see the cable or the rope, and the rope and pulleys, and that's applying a tension. And it's holding the broken ankle or broken leg in equilibrium. Last thing you want is for the brake to keep moving. You want it secured so that the bone will heal. So you're going to keep the leg in equilibrium by applying a tension. Two tensions, T1 and T2, all created by this little mass at the bottom. So we'll, as we get into this chapter, we'll solve this problem that's shown on the cover slide. And let's move on to our outline here. So we'll see our frictional forces, and then we'll learn about strings and springs as they apply to Newton's laws too, and then translational equilibrium. The equilibrium, that's what we mentioned in the last slide. Translational, basically everything that all of the motion we've been talking about so far has been translational motion. We're going from point A to point B in a straight line or some combination. So we can either be going a straight line this way or this way, or some combination of the two. So that's translational. The other type of motion is rotational, and we'll see that in a few chapters. But so far, these 6 chapters have all focused on translational motion, or the motion from point A to B. And so looking back at our picture over here, why is this translational equilibrium? Because we don't want the bones moving while they're trying to heal. So we have a broken bone here, and we want to keep some tension on the foot to allow the bone to set properly, and we want to keep it in equilibrium to allow the bone to continue healing. So, and then last 2 topics are connected objects. We'll revisit that. And then circular motion, we'll introduce that as our precursor to rotational motion, the 2 of which are very different. So we want to refresh our memory on a couple definitions here. So weight in particular is the weight of an object on the Earth's surface. The weight of an object that's on the Earth's surface is the gravitational force exerted on that object by the Earth. So our equation is shown in this form here because it's just like it's the same as our Newton's equation, F equals ma, and here the force is the weight. So here our force is weight, and then our acceleration is going to be the acceleration due to gravity. So that takes us to our more common definition or equation that we used already, is that weight equals mass times gravity or gravitational acceleration. So whenever we do talk about weight, it always will be in the form of W equals mg. Weight is a vector, mass is the scalar, and then of course acceleration is a vector as well. And here gravitational acceleration has one direction. It points towards the Earth, towards the center of the Earth. So sometimes weight is called gravity force or gravitational force. So when you hear that, actually gravitational force is the force due to gravity, but gravity force is often the term used for weight. So mass is a measure of how hard it is to change an object's velocity. Remember that velocity is a vector that has a magnitude and a direction. So mass, if mass is a measure of how hard it is to change, if it's a measure of how hard it is to change the speed, you're still changing the velocity. Mass is a measure of how hard it is to change the direction. So you're still changing the velocity. And then, of course, mass is a measure of how hard it is to change the magnitude and the direction. So if you change one, you change the other, or you change velocity. So velocity, again, is magnitude and direction. If you change magnitude, you've changed velocity. If you change the direction of the object, you've changed the velocity. If you change both the magnitude and the direction of the motion of the object, then you've, of course, still changed the velocity. So the point, again, is that you can change one and still change the vector. If you're traveling in a straight line and then you go around the bend, you've changed direction, so you've changed the velocity. You can stay on cruise control and go around the bend, so you kept your speed the same, but you changed your direction. So again, you changed your velocity there. And then mass is a measure of the amount of something that you have. It's a measure of the quantity of matter that an object has. And the more matter or the more massive an object is, the more difficult it is to change the velocity. And changing that velocity also includes stopping entirely or starting. So that's where Newton's law comes in. An object at rest will stay at rest unless an external force acts on it. An object will stay in motion at a constant velocity unless an object intervenes to stop it. So those external forces, unless something intervenes to stop it or start it or change the direction or change the speed, all of that is a force. So an object in motion will stay at motion in the absence of a net external force. But if there is a net external force applied to it, the object will change. It'll change direction or it'll change speed depending on what you're doing to it. Change in direction. You think of two billiard balls that collide with each other. They're going to change direction based on that collision. So a little different. Again, the forces that are being applied to the object can either change the direction, it could change the speed, or it can change both. It could also stop the object, or it could start it. So again, that force is a push or a pull acting on an object as a result of the object's interaction with another object. Earlier, so in this case here, so we can think of the two billiard balls, obviously objects. But in the last lecture, we said the object's interaction with its environment. So it's the same thing. The environment is an object. It could be the wind, or it could be another physical object, anything there that you're interacting with. So that push or pull is going to result of is a result of the object's interaction with its environment or its surroundings or with another object. So forces, they're a push or a pull, and that push and pull falls into two categories. One of two categories. So our first is contact forces, a generic term here, and it's in the last chapter we saw contact forces that were between two boxes. We had, or three boxes. We had that example, and here's the contact forces right there. But what this list is talking about, it includes that contact force that we already saw, but it also includes friction, tension, all the things you see listed here, because for each of these forces, you're in contact with something else. So with friction, think of friction is what slows you down when there's something going on. So think of like the baseball player sliding in the base. The baseball player is in contact with the baseball diamond, and and the dirt. And the dirt, the friction between the dirt and the baseball player is what slows the player down. So the baseball player is in contact with the field. Tension is a contact force because think of tug of rope here. You have two groups on each end pulling on each end, and that creates a tension. You can also think of the cable in the picture. It had the weight hanging on it, and that created tension. Same thing with a bucket in a well. The bucket's going to hang from the cable, and that creates tension in the cable. And then there's the normal force. We saw that one as a support force, where it's more of a structural support force, so it's always perpendicular to the surface on which the object is resting, so it's holding it in place, giving it some support. And then air resistance is a force. It's a force of nature, obviously. When the wind blows against the leaf, there's air resistance that slows the air down. Like when it hits the leaf, that leaf is going to push back on it, and so consequently you'll see some air resistance there. And then applied force, that's the force that's often when you see a question that says a force is applied, a force of 7 meters is applied, or a force of 7 newtons, not meters, newtons are force. So a force of 7 newtons is applied to the object, and the object gets an acceleration. So that applied force could be you applying the force to something, or it could be anything that set it in motion or changed it. Typically, though, the applied force is usually a person that's intervening. And then the last part's spring force. We'll get into a little bit of that here, and then we'll study it more in a later chapter on equilibrium. And oscillations actually in that chapter. So basically the spring force is that you have a spring, and it doesn't create tension. Like the spring already has tension in it, or tautness, or a measure of tightness. But the spring itself can be stretched or elongated. So, and then it could exert a force on a block that it's attached to, or whatever it may be. So the spring force is going to experience a force as well as push one or let something hang from it, like another not a support force, but similar to tension. The spring force is similar to tension, but of course, tension's on a rope and spring force is obviously on a spring. So the next, so that's our first category of contact forces. The second category is at and distance force. So gravity is at a distance. It's generated at the core of the Earth, and it's holding us onto the surface of the Earth. So there's a good amount of distance between us and the center of the Earth. So gravity is an at a distance force, and then so is electrical and magnetic. Lightning can strike something. Or even just lightning being in nearby, it's enough to shock you or cause some damage. And then magnetic force obviously draws magnets to each other, or magnetic material to the magnet. So this chapter is focusing on frictional and tensile forces, so friction and tension. So again, tensile is tension. So frictional force is a force exerted by a surface as an object moves across it. So again, that's the baseball player sliding in the base, or the ice skater skating on ice. The ice has not a lot of friction, but enough that would cause if you fell on ice, you eventually slide. Like if you were in a skating rink and you fell on ice, you would eventually slide to a stop with the little bit of friction that it does have. So again, frictional force is force exerted by an object or by a surface as an object moves across it. So friction results from the two surfaces being really pressed closely together, and it causes intermolecular forces of attraction between the two surfaces. So that's really basically these ridges right here, these intermolecular forces of attraction right there. So we call them forces of attraction, where let me move the slide up here. So I'm going to get back to the this bottom bullet first. So sliding the box over the plate requires a force that's large enough to overcome the resistance of that surface's irregularities. And that resistance is the frictional force. So the box, it looks like, we say up here, forces exerted by an object moving across it. So we want to get this box to move, and so we have to overcome a threshold to get that box in motion, and that resistance is a frictional force too. So we have an object in motion up here, so that's going to be our kinetic friction, and an object that's being held in place by resistance, and that's going to be our static friction. And I think that's what we get into. Yep, that's our next slide. So we have two types of friction, kinetic and static. So kinetic is the friction of motion, and it occurs when surfaces are sliding against one another. The baseball player sliding against the dirt, the ice skater sliding against the ice, the book move or the box being pushed across the table. So the surfaces bounce along relative to one another, and no bonds are actually formed whenever we're talking about kinetic friction. So kinetic friction tries to stop the surfaces from moving. It is a type of resistance, and again, they're stopping the surfaces from moving. But static friction, on the other hand, prevents the motion from starting. So static friction is friction that prevents the two surfaces from moving relative to one another. So here you do get strong bonds between the surfaces. Static friction is much stronger than kinetic friction. And again, the two surfaces can form a connection or a bond. That intermolecular relationship we talked about in the last slide, that's what's happening here. So if you have a windowsill, say you have a little windowsill here, and you have a vase that's sitting on the windowsill. So the vase is sitting on the sill, and you want to move it, and you have to pull real hard to get it unstuck. A lot of times people think that that's the paint on the windowsill holding it in place like a glue, and there might be some truth to that, but really what's happening is the vase is forming a bond with the material, whether it's the paint or the underlying structure of the windowsill, forming a bond there, and then when you have to overcome to get it to move or to just simply pick it up. So there are two types of friction, and a key thing to note down here is that both of our friction forces, kinetic and static, are proportional to the normal force, and both have direction opposite the direction of motion on the object. So if the object's moving this direction, friction's moving in that direction. Object moving this way uphill, so like maybe you're climbing a pole, friction's going to act downward. So friction's always in the opposite direction of the motion, and friction's always proportional to the normal force. So that's what our first equation says right here. Our kinetic friction force, its equation is mu sub k n. So F sub k, this F sub k right here, that's our kinetic friction. It is a vector, but we're not writing it in the normal vector form because it's always opposite direction of motion. It's never, you're not going to see an x and a y component. You're just going to see it in the opposite direction of the motion, that one component there. So if friction is a kinetic friction, a lowercase letter here, it's the only one, it's the only force that we'll write in lowercase. And then you can see the proportionality to the normal force, where normal force is right here, directly proportional. So the normal force increases, so does F sub k. So they're directly proportional the friction force is directly proportional to the normal. And then this mu sub k, that's the coefficient of kinetic friction. And the coefficient of kinetic friction, it's a dimensionless number, no dimensions to it, and it's always positive, and it ranges anywhere from 0 to 1. So ice is closer to 0 with very little friction. But then the greater the number, the closer to the number 1 you get, the greater the friction. So something that has a coefficient of kinetic friction of a 1 is going to be extremely difficult to move. So since the coefficient of kinetic friction is always a decimal or fractions between 0 and 1, so our little example here is if mu sub k equals 0.1, the force of kinetic friction then is 1/10 of the normal force. So we would just plug in 0.1 right here, and we see our kinetic friction is equal to 1/10 the normal force. So kinetic friction, just showing you those concepts again. It's proportional to the magnitude of the normal force, so it's going to be directly proportional to the normal force, but its direction's opposite the direction of motion, and that's what we have right here. The F sub k is this way, so motion must be that way. And here it's perpendicular, it's proportional, and the normal force is perpendicular to the surface on which the object is sliding. And then, of course, you have the weight coming down too, pointing towards the earth, or center of earth, actually. So our kinetic friction is proportional to the magnitude of the normal force, but its direction again is opposite to the direction of motion. So its direction is perpendicular to the direction of the normal force, but the values are directly proportional. So here we have our direction of motion right here. So this is our direction of motion. Let me make that a little darker. So this is our direction of motion that we can see from this applied force right there. And here's our spring, and the spring is pulling the block. And there's our F sub k in the opposite direction of this motion. And it's perpendicular to N in the diagram, because N is your support function. N is the support force that's perpendicular to the surface on which the object is moving. So it's always going to be perpendicular to F sub k, but then in the equation they're directly proportional. So perpendicularity and directly proportional don't have any effect on each other. So we see here, add in a second brick doubles the normal force, which doubles the force of kinetic friction. The more mass you have, the harder it is to get it to move, or the harder it is to slow it down. So you're going to double your friction there when you double your mass, because it's going to take more effort to slow the object down, or get it moving. So kinetic friction, an object moving in relation to kinetic friction in relation to Newton's first law, is that an object moving with constant velocity continues to move with the same speed and in the same direction as long as no net force acts on it. Well, kinetic friction is the force that's acting on the object and bringing it to a stop. So key concepts about kinetic friction, kinetic friction is independent of the speed of the surfaces. So no matter how fast or slow the objects are moving, kinetic friction will always be the same. So we can tell that kinetic friction is independent of the speed of the surface by looking at the equation. So if we take a look at our equation here, is there an area in this equation? No, there isn't. And is there speed in the equation? No. The only thing in this equation is mu sub k and the normal force. So the dependency of the friction, kinetic friction is dependent on the normal force and the coefficient of kinetic friction. So they're the components or the variables that are in your equation. They're your dependencies. So if it doesn't show up, if a variable is not in your equation, then like in this example here, our f sub k, there's no value, there's no speed in the equation, there's no velocity vector, so, and there's no area. So kinetic friction is independent of the speed of the surfaces. The velocity and speed are not a part of the equation. And same thing with area, independent of the area of contact between the surfaces. So no matter how big or small the area of contact is, f sub k is going to be the same. And again, we can see that in our equation where area is not a factor. Area is not a part of the equation. So f sub s consequently does not depend on it. But here's another thing, another graphic that'll help to understand those concepts on the last slides. So the two gentlemen here, the New York Yankee, that's Aaron Judge. This is Aaron Judge. And the Houston Astros player is Jose Altuve. And this picture was taken about 2 years ago, I think, at the All-Star game. So both All-Stars, and then I think both of them were in the running for MVP of either the All-Star game or the series, I think. Or I think it was the World Series that they played against each other. But at either rate, both were contenders for the for MVP, and Altuve actually was the one that won. But anyway, the point or the tie in the kinetic friction is that Aaron Judge is the tallest player currently on the active roster in Major League Baseball, and Jose Altuve is the shortest. So we have the two extremes here, and yet no matter what their size is, kinetic friction is going to be the same. It doesn't matter how fast either of them are. It doesn't matter. The area doesn't matter. Like when they slide in the base, the chest area right there, it doesn't matter. It doesn't matter who's taller or who's shorter, who's broader. The area is irrelevant. They're both going to slide the base with the same friction force. F sub k is going to be, it's going to give them the same, that kinetic friction equaling mu sub k times the normal force is going to be the same for both of these players. So we would need to know mu sub k for their jerseys. And it's going to be probably the same material, so it'll be a mu sub k for each. And then the normal force is the force that the Earth is actually exhibiting or applying as they slide in the base. So that's all we would need to know. Maybe so mu sub k is on a scale of 0 to 1. Perhaps the uniform is about a 5. Probably actually hopefully a little lower. You kind of want them to slide easy. You don't want friction to pull them to a stop prematurely. You want them to get the base. So uniforms are probably made a little bit more silk in them. That's a little slipperier, and then so consequently they'll continue sliding as much as possible to get to the base. So all we need, though, for our kinetic friction equation is mu sub k and that normal force. So we don't need the area, and we don't need the velocity, or speed in which they're running. None of that. All we need is mu sub k and n. So our first example here for our kinetic friction is that we have a child sliding down a playground slide with an acceleration of 1.26 meters per second squared. And then we want to find the coefficient of kinetic friction between the child and the slide. And here we're told that the slide's inclined at an angle of 33 degrees. That's 33 degrees below the horizontal. So our first thing that we do is we draw our coordinate system, and then we will draw the slide on there too. So I'm going to draw, so we have our coordinate system, and our first inclination is to say, well, the wording said 33 degrees below the horizontal, so that must be here, right? So I'm just going to include this out. But if we do that, if we do that, and then we set up our slide, was a child sliding down a playground slide. So this is the sliding part. So if we just drew that right up here, if if we made the slide here and the body or the child is sliding down, well, the forces that we have to take into consideration, we need that normal force. We're not told what the normal force is. So we know that the normal force is perpendicular to the surface on which the object is moving. So that means our normal force is right here. It's perpendicular to that one. So this would be N. And then we also have weight in the picture too. So weight comes down here. So if we were to draw that, if we were to overlay that on our chart right here, we get weight right here, and then the normal force right there. And but look what happens though to our triangle. It kind of gets all out of whack, and it does nothing's nice and neat now. Doing it if we did things this way. So what we want to do is we want to change our coordinate system. So we're gonna this is our 33-degree angle. So we're gonna rotate our coordinate system 33 degrees. So when we do that, our new coordinate system now is this one right here. So we just simplified things a whole lot. Because by rotating that coordinate system, well, what we did, we rotated it by 30 degrees. So now we've got this as our 33-degree triangle. And I'm going to make my vector a little longer here. And then we have this part right here. As there's our actual triangle that we want to use now. So when we do that, when we set it up this way, now we can take a look at our normal force now is entirely along the y-axis, and then W is going to have components of each, x and y. So our forces here are obviously F sub k, our kinetic friction, entirely in the x direction, or negative x direction. And then we have our normal force, which is directed upward, entirely in the y direction. And then the weight is at an angle with the y-axis, which is now the not the y-axis, the x-axis here. Let me move that there. So weight, this is y, and the normal force is only in the y direction. F is going to be in the negative x direction. And then when we take a look at our triangle here, our forces are we want to sum the forces in the x and y direction. And even though we're trying to find F sub s, we have to basically, we're trying to find F sub k. So it's unfortunately not as neat as just going right to the F equals ma equation and solving, going right over to this equation here, or mu sub k times n. Unfortunately, it's not that easy. We want to find mu sub k, but we don't know what n is, and we don't know what kinetic friction is. But we do have an acceleration though. So that's a hint that we want to get back to that F equals ma equation. So our W again is at an angle with the y-axis, and then the x-axis too has a component there. So we want to sum our forces in the x and y direction. So for F sub y, we're going to have our normal force in the y direction. And then our weight in the negative direction, so that's mg. But the y component now, the y component's right here, so that's the side that's adjacent to the angle right there. So so that's our cosine of theta equals ma. So so now what we can do is we can actually try and solve this. Ma goes to 0, and because it's only we're only interested in gravity, the force of gravity pulling the child down the slide, and So now we can actually solve for n. So n is equal to mg cosine theta. So we put our mg in. So just a recap, ma equals 0 because there's no acceleration in the y direction. It's all in the x direction. Like we can see right here, the child is sliding down the slide in the x direction. And we want to find f sub k. So this is going to become our first equation. It's our first equation right here. And then we want to solve for f sub x too. So the forces in the x direction, we have the opposite side over here. So we have, and then remember this is the weight right there. That's the hypotenuse. So the force in the x direction is going to be the force right down in here. That's parallel to this one up here, and that's going to be mg sine theta, and then the next thing we need is in our x direction is this coefficient of friction. So that's where our kinetic friction comes into play. So we can put mu sub k times m, and then that of course equals ma. So these are our forces right here. That's a force and that's a force, and then the force has to equal the ma. So when we see our two equations for x and y, we want to be able to solve equation 2 for mu sub k. So let me fix that up a little bit. So now we want to actually go ahead and solve equation 2 for this m sub k. So we'll come back over here and we'll put our mg sine of theta minus this ma. We're going to bring that over to this side, equals our mu sub kn. Mu sub kn. So now we're going to solve for mu sub k. So this is going to come over here, and we'll be able to solve now. So we'll be able to solve now by putting equation 1, this equation right here, in for the value of n. So I'm going to erase n over here, and then I'm going to put in the value. So it's mg cosine theta. And so now I think we're ready to actually, we want to rearrange it now. So we can take that value and plug it in here. So our value of n is mg cosine theta, and that keeps mu sub k separate right there. So now we're able to actually start solving for the problem here. So we're able to pull the mass out. I'm going to erase a lot of this. Be able to write on it. So back to our equation here. We have our mg sine theta minus ma divided by mg cosine theta. So we can factor the m's out, and we'll factor the m out, and we have g sine theta minus a over mg cosine theta. So the m's are going to cancel each other out over here. So static friction, that force is a preventive force. It prevents two surfaces from sliding against one another. Static friction keeps an object from starting to move when a force is applied. So static friction, again, it keeps an object from starting. It resists it from starting. And kinetic friction is the friction that brings it actually to a rest. So kinetic is motion. So the object is already in motion, and kinetic friction brings it to rest. Static friction, it's at rest, starts at rest, and you need a maximum value to get that object to begin moving. So static friction force has a maximum value and can take on any value from 0 up to whatever that maximum is. So the maximum is different for every scenario and every object. So once the maximum value is exceeded, the object will move. So that maximum value acts as basically a threshold value. So Newton's law is an object at rest remains at rest as long as no net force acts on it. So static friction allows the object to stay at rest. Kinetic friction is the object in motion and it brings it to a stop. So static friction force, same equation, just a different coefficient of static friction now. We had a coefficient of kinetic friction. Here we have a coefficient of static friction. And then, of course, we see that the max, when static friction is greater than or equal to 0, or less than or equal to the maximum value for static friction, then the object will not move. But once we get over that threshold, then the object is going to move. All values greater than F sub S max will make the object move, and that's when actually that's what. Or, I'm sorry, all values greater than F sub S max. That should say right here. So F sub S max. That's this here right. The comma makes it look like greater than F sub X, but it's all values greater than this value here. The F sub X max is what's going to make the object move. And once it starts moving, then kinetic friction takes over and will bring it to a stop. So static frictional forces are independent, same thing as kinetic, same set of principles, independent of the area of contact between the surface. They're independent of velocity. They're also parallel to the surface of contact. And so if you have your surface of contact right here, if your object is right here, it's going to move in the opposite direction of motion. Force is this way. Here's your F sub S. So just like F sub K, they're both parallel to the surface of contact, and they're both in the opposite direction of motion. So the figure below here shows the object at rest, and it's independent of velocity, and we're showing velocity here, that we're showing it to indicate that it's at rest right here. So you have your static friction is 0. Basically, you have your object right there, and then so it's at rest right here. And then here's where when you have it greater than 0, you'll see a velocity of 0 here, and the force again is being applied. So it's starting to give. Actually, let me start that again. The top picture here, there's no force that's being applied either, so everything's at rest. And then down here you have a force that's being applied. It's still at 0. Velocity is still at 0. And but this with this force of pulling this way, this surface here is basically holding it. It's pulling back. So you're pulling. You're actually exerting a force, but you didn't overcome the max yet. You're just greater than zero, but you're still less than the threshold value or less than the maximum. But then when you get up to the maximum value, right at that max, you're still at a zero velocity, but you can see the force got bigger right here. These forces got bigger. But then once you exceed that maximum, once the object is sliding, friction's now kinetic. So just as soon as you get over that max, exceed that, the friction F sub S turns to F sub K, and kinetic friction takes over. And kinetic friction has a magnitude that's smaller than static friction. It's again magnitude. Both of these are heading in a negative direction. But when you look at the magnitude, the value of static friction is less, or the value of kinetic friction is always less than the value of static friction. So again, kinetic friction is greater than, or kinetic friction is smaller than static friction. So friction, static friction is the one that's basically keeps your tires on the ground, keeps your wheel on the ground, it helps you gain traction. And friction, again, static friction in particular, provides traction between your foot and the surface or between the tire and the road. The force provided by weight alone, that's not enough to cause motion. That's pretty obvious if you're standing on ice. Not even with ice skates, you stand on ice with your bare feet or with shoes on, and you could still fall. So it's not enough to hold you or anchor you to the ground. Static friction is actually what's necessary to keep you to be able to walk on the ice or walk on the road or whatever surface you're on. So here's our comparative table between friction forces. We see kinetic friction is always smaller than static friction. So static friction is the larger of the two. Static friction is greater than mu sub k. So this is the table when we don't have to calculate a lot of the problems we're going to be using. For now, we're going to be solving for one of these friction coefficients. But when we're solving for something else and have to take into account friction, this is the table that we'll refer to, unless the problem outright tells us what the coefficient is, and then we would use that value. So our first problem here, or our next problem with friction. So for this problem, we want to know the minimum horizontal force. So that's the minimum force in the x direction that's needed to make the box start moving. And we're given two coefficients, or we're given each coefficient, and we just want to know the minimum horizontal force. So we see that it has a horizontal force right here that's applied to it. That force is entirely horizontal, but then this force is two-dimensional. It's a combination of force in the x direction and a combination in the y direction. So perhaps someone is pulling this box, and then the arrow right here is that maybe someone else is leaning on it and trying to impede that motion. So we have two forces acting on the box, and one is two-dimensional, one is one-dimensional. And we want to find the force, the minimum horizontal force needed to make the box move. So that minimum horizontal force is going to be a combination of this force and this force, so a combination of the two. So we'll start out with the summation of our forces in the y direction. So remember that motion in the x and y direction are independent of each other, and we'll sum all the forces in one direction, and then sum all the forces in the other direction. So we're starting with y here in the y direction. So so we have our normal force right here, and then we have our weight, and we have friction, but that's what we want to find. That's what we don't know. But we have we'll be able to calculate the weight based on the kilograms right here. and then we'll calculate the normal through our equation setup. So our summation of forces in the y direction is, we know it's N is one of them, and then and then we and then we know the weight is the other. So weight's going in the opposite direction. That's in the negative direction here. Normal is in the positive, and then we have the x component right over here of this force here, or I'm sorry, the y component of this force, the 16 Newton force. So and notice that this force right here, this force right there, that's an applied force, and so is this one. So we're going to write this. We're just going to call this an applied force in the y direction, and notice that it's also in negative because the arrow is pointing down. So it's pushing. This one is a pull, and this one's push. Now, if you're thinking back, well, I thought we couldn't have a push-pull. That's true. You won't see a push-pull in equal and opposite reactions. So for Newton's third law, equal and opposite reactions, you won't have push-pull. It'll always be push-push or pull-pull. But this problem is not a equal and opposite reaction. This is this one's Newton's law that an object at rest will stay at rest until a net external force is applied, and it'll make it move. So a net external force is being applied, and will make it move, and then we're going to find the friction force to make it move, and then the friction force to bring it back to a stop. So that's why we can have a push and a pull here, because it's not a reaction problem. So our applied force is going to be in the y direction here, and that's going to be a negative. And then, so this is our F right here. This is our F equals MA. And the box is not accelerating. It's not moving yet. So there's no, and even if it was moving, there's no motion in the y direction. So we'll put our coordinate system here. So the box is only moving in the x direction. So we're looking for the vectors in the y direction. And so A is actually 0 in the y direction. So now we can solve this equation for n. And with that equals W plus our applied force in the y direction. And then we can actually figure that out. So n equals our 28 kilograms here for the weight, 28 kilograms times 9.81 that meters per second squared due to gravity. That's our weight, plus 16 newtons times the sine of 55. Because remember, we're only looking at the y components here. So that equals 288 newtons. And then, and it's positive because we already accounted for the negative sign in the equation. So right up here, remember that this is a sum. The sigma, that's a sum. So normally we're adding everything. So what we did was we added a negative. So because we already put the negative up in the equation there, we don't put it again down here as a negative. So now we can go to our x direction and sum all the forces in the x direction. So that's our F sub s right here. So that's and that's going to be negative. So friction is going to be negative. So it's in the opposite direction of motion, and there's our coordinate system again, positive x, and then we have the x component of this force up here, and so this is going to be our applied force too, and it has an x component, and it's also in the negative direction there too, again because that arrow is pointing in the negative. And that's going to be our cosine 55. And then we have this force right there. So that'll be we'll just call that F right there. And that's entirely in the x direction, so we can put that down there or just leave it as it is without the x down here. So again, that's our f. This all constitutes a summation of our f's in the x direction, and it equals ma also. And also here, a is 0. It's not moving yet. We want to find what that maximum is. So we got to write that max down here, f sub s max. So that's going to be, this drops out to 0. And then, so both initially at rest. So now we can solve for, the force that has the maximum force, or I'm sorry, it says what is the minimum horizontal force needed to make the box start moving. So we have, we can substitute our f sub s max in, and we know what that equation is. So we have that as our mu sub n, mu sub s, and it's a negative there, times the normal, plus the applied force, times the cosine of 55, equals this f value, f, right here. So now we can plug our numbers in, and we have our So I'm going to erase this because we solved this problem up here. So we're solving for this f. So that's already positive, and we set it equal to 0. So we're just bringing these two, f sub s max and this one, over the other side of the equation. So that's why we got rid of that mu sub s, the negative part there. So now we can put in our values. And then the value we solved for n is 288 newtons, plus our 16 newtons times the cosine of 55. And that comes out to a horizontal value of 127 newtons. So the force that gives us the maximum threshold to slide the box, that's our 127 newtons. And we got to exceed that force to get for the box to get moving. So the minimum to start moving is 127. I think, did I say that was the max? We found our f sub s max is this one right here, and the force needed to overcome f sub s max is this value, the 127 that we just calculated. So this section is an application of Newton's second law. So the second law is our vector f, or force, equals mass times acceleration. So the key to remember here is that force is a vector, and so is acceleration. And the direction of the acceleration is in the direction of the force. And the interpretation of this equation is that a force is applied to a mass, and when that force is applied to a mass, it's going to accelerate. So in the literal mathematical interpretation is this the one right here. It's just a rearrangement. But again, same thing, just a key concept is that the second law is about acceleration. Force is secondary in that definition. So a lot of times on the exam, a question similar to that is about the second law, whether it's about acceleration or force. And everybody always puts force, but it is not. The first law is definitely all about force. Second law is predominantly about acceleration, and it's the application of the force that's going to make it accelerate. So force becomes secondary in that case. And then the equal and opposite reaction in response to two forces from different objects is obviously the focus of the third law. So here in section 6.2 with strings and springs, we're going to look at the second law as it applies to both strings and springs. So they're physically different, and they're going to be different mathematically as well. So we're going to start out with strings, and when you pull on a string or a rope, so anything that's not a spring, it's going to become taut or tight, and that's what's happening here. You see the two hands pulling these opposite ends, and there's no play in it. They're taut right there. Same thing if you're playing tug of war over here, you're going to have the strand is going to become taut or tight. And that tightness is defined as tension. So tension is that tautness. And again, tension is a vector, and tension is also a force. So it's a type of a force. It's different than an applied force. That's more generic when you're pushing or pulling. But tension is specifically a force that's on a string or a rope. And the tension on a string pulls equally to the left and equally to the right. And so if you're pulling here, if you're pulling this way, it's all equal, assuming the same thickness rope. But right there in the center is where the tension starts to really, you're pulling really close. If we looked at that as a center, you got pulls in opposite directions. So that's usually the break point. So if you either broke it right there or you cut the string right there, then the tension is the force to pull the two ends back together again. So when you have the solid rope right here, and you're pulling on equal ends, you have pretty much a break point in the middle. And if it did break, then both halves go limp. And if you took the two halves and pulled them back together again, then you get two separate tensions. You get a tension, you get a tension over here and a tension over here. So strings are really good with using in combination with a pulley. And so if this guy here was trying to pick this crate up, like let's just say he was standing next to it, and he was trying to pick it up. Even if he was trying to pick it up with both hands, it would be really hard. It would be very difficult. And even if he could lift it and carry it, like lift it up enough to walk a distance and place it back down, he still would not be able to lift it overhead. I mean, that looks like a pretty sizable crate. And so lifting it overhead to put it on a shelf or something, or on a flatbed of a truck or something like that would be very difficult. So the pulley system is used where he could lift it, and then say there was a truck back here. Let me erase this part here. So let's assume there was a pickup truck back here, a little flatbed right there. And he pulls the box up high enough to clear the bed right here. Then somebody else could actually push it over and then unlatch it. So the pulley is definitely a way of helping somebody. The pulley in conjunction with the tension in the rope is a great way of assisting people in lifting a certain object, or keeping continuous tension on something like the foot in the cast. So the ideal pulley, though, the word ideal, what we mean by an ideal pulley is that the pulley has no friction. So a lot of times when we were talking in chapters 1 to 4, we were talking about friction-free environment, or working in a vacuum was the common term then. So when we're talking about a vacuum or outer space or friction-free environment, that's our ideal situation. And so our ideal pulley has no friction in it. So, or it's and typically that's a good approximation, because any pulley, the friction's negligible. So because the inside track of that pulley is so smooth that it really doesn't provide much tension. And if it were rough, you could put oil on it or something like that to make it more like an ideal or perfect pulley. So the ideal pulley changes the direction of the tension in the string without actually changing the magnitude of the tension. So what that means is, if we get back to having this crate here on the ground, if we put our crate here on the ground, and we still have this rope attached to it. We still have this rope. So again, if we get this guy standing here and he's lifting it up, it's going to have tension in the upward direction. It's going to, but it's going to be entirely upward. All of the entire. Let me draw that a little neater. The entire pulley. So the entire pulley has, if he's pulling on it, he's lifting it up, the entire pulley, the entire length of that string or cable or cord, whatever you want to call it, the tension is all in one direction. But when you put a pulley in there, when you put that pulley in, right, like it did right here, now the cord, instead of being entirely straight, it comes up and down. So here's where your pulley is. So it goes up over here, and the cord comes down. But here in this picture right now, the second half or both halves of the cord are limp. Nobody's pulling on it. But if you put the guy over here and he starts pulling on this string, that's when you get tension. That instead of again having it all in one direction, it's now both. It's still both in the upward, but the direction of the cable changed. Now you got the cable looping around, and you got the cable looping around that pulley, and consequently, it actually instead of if we had it straight. If in the first example when it was straight like that, that would mean if we just dropped it around, the tension should go that direction. If it's kind of all the tension this way, but the pulley actually reverses that tension, so it puts the tension pushing this way. Upward, and then this tension also upward. So both the tensions here are upward, and then consequently, if you let go of the rope and it goes back this way, you still have a tension going up that way. So you now have tension in two directions here, as opposed to just straight, just in one direction or straight up. So the ideal pulley changes the direction of the tension without changing the magnitude of the tension. It just changes the direction. So we're going to do a little problem here. We'll look at a problem, and it's you're pulling on a rope, and you're going to lift the bucket of water from the well. And you're given an acceleration of 1.24 meters per second squared. And we want to find the tension in the rope. So we start out with the things that we know. So we know we have the mass. We know we have the mass of the bucket of 7.27 kilograms and an acceleration of 1.24 meters per second squared. And then what we don't know is our tension. And we know that the representation here, or the an equation of Newton's equation. I mean, the title of the chapter is Newton Applications of Newton's Law. So this is the only equation in Newton's Law. So we know we want to use that. So we know we're going to use the Newton equation, Newtonian equation, F equals ma, and we want to, and we'll see later. As we progress through it, we don't know for sure that we need a kinematics equation. Right now, it's just saying what's the tension in the rope. So that looks like we can take this F equals ma equation, and maybe change it over to here, tension equals ma. But so we know we want tension, but let's draw our picture first too. So we're pulling on a rope to lift a bucket of water from a well. So we have our well, actually that's not big enough. So we have a well here, and then we have a little bucket, and we're pulling this bucket out of the water here. So the cord has the tension in it. So when we look at it that way, when we see this picture here, we'll draw our coordinate system here. So this is upwards, so positive y, and this is positive x. But the neat thing about, even though we're changing direction, it's not really putting a two-dimensional part into this. I mean, we can go back if we get back to actually this slide here. We can try and say, well, is this a? We can try to say, is this a right triangle here? Well, that's a big arc, so we can't really approximate that. It would not be accurate if we made that a point particle right there. It is a little too, I mean, we could try, but we don't really get anything gained out of it because the tension's the same on both sides. We have tension here and tension here, but then that violates our vector principles where the hypotenuse, this tension, is equal to the tension in the x direction plus tension in the y direction. And, or actually, I'm sorry, I said it violates that. It actually doesn't, because if we made these two the same here, then what we would really say is that this tension in the x direction falls out. So we have the tension on the hypotenuse equaling the tension in the y direction. So that's what we're going to use on the next slide here. We don't have to worry about drawing our triangle. We just want to say that the tension is entirely in the y direction here. So we'll go ahead here, and we know that our next relationship is that force is always summed up. When there's multiple forces, it's always a summation, and we're going to sum them all in the y direction. So if you're thinking we have two tensions, again over here and over here, well, remember that the tension, only the direction changes, the magnitude does not. So because the magnitude is the same, we only put the tension in once. So what are we adding to that? Well, we're adding the weight. We're adding the weight of the bucket here. And this mass, being given a mass of the bucket, that's pretty much an indicator or a little clue that we might want to be needing that for something beyond this F equals MA. Because again, we know that the weight is always mg. So we end up with our summation here, F sub y. We're going to sum our tension, and then we're going to add to that our weight, and the weight's in the negative y direction. So we could have just wrote that as tension minus W. We could have done that. And then, so there are forces, and force equals MA. So we have force equals MA, and then we have that the weight equals mg. And again, we don't have to put the negative sign in for g because we just did that up here. We just took that into account. So this equation right here, we don't need to put the negative sign there again. So we can take our tension equation now. That's this equation. So we'll take this equation right here, and we'll plug in the weight, and we'll solve for t. So let's just rearrange that. We got t equals, so we move this negative w over the other side of the equation. So that gives us a positive mg now. Positive weight equals mg. And then our MA, that's already over on that side of the equation. So we can simplify a little bit and say that, actually let me erase this, move it over for room. So we have here T equals mg plus MA. And we can simplify that a little bit by factoring out the m. And then we have our g minus a. And we don't need to put the little vector on top of the g. And then, so now we can go ahead in and plug our numbers in. So our T equals our mass. Our mass is 7.27, and that's kilograms. And then our 9.81 meters per second squared, minus the acceleration of 1.24 meters per second squared. So that gives us a tension. Equal to 80.3 newtons. So another question I want to ask you here is, what if you double the tension? What happens to the acceleration? So that's not part of the problem, but I did put that in the solution because this is another one of those MCAT type questions where it's a relationship dependency. So when we say what happens, the question is again, what if you double the tension? What happens to the acceleration? So we want to get back up to equation A up here, and we see tension over here and acceleration over here. So they're directly proportional. They're directly proportional. So we know that both of them, if you double the tension, the acceleration is going to increase. But let's see if it actually does double. So if we take this tension of 80.3 newtons over here, that's what we just solved for, and we double that, our 2 times our tension is 160.6 newtons. So let's put that number in our next or in our equation, and particularly we want to go into this one now, this equation down here. So if we want to, let's substitute this 160 in and see what we get. So we put this number in for the 2 t's. So here where we solved, so this equation down here, so this equation right there, we solved, so we just take this 160 right here, and we want to put it in there and solve for A. So we have our 160 newtons equals our mass of 7.27 kilograms times our 9.81 meters per second squared minus the acceleration. And when we solve for A, right here, we're going to get that A actually equals. Let me change a color here. So when we solve there, A actually is going to equal 12.28 meters per second squared. So originally it was 1.24. That's what we were given up here in our problem. We were given 1.24, and we equated to which equated to a tension of 80.3. But when we doubled the tension, the acceleration did not actually double. So that's what we would expect to happen when we see. Actually, let me make this a different color here. So we would expect in our F equals ma equation, or T equals ma, we would expect a 1-to-1 relationship. You double T, you double A, because we're holding the mass constant. So it would look like that should be what happened. But in effect, it didn't double. So the reason for that is that we've got, it's not, the equation's more complex than this T equals ma. We have 2 accelerations to deal with. We have the regular acceleration, that the letter A, that's going to result from when you come over here and you pull on the cord. So when you pull on the cord, you're creating this A acceleration. And then we're working against gravity, that 9.81. So we see that we're subtracting the weight from the tension in this equation, and then and added the weight to the acceleration in back over here in this equation down here. And so it's, even though it's proportional in this equation, it's not a direct 1-to-1 correlation. Double one, you double the other kind of thing. So here what we can say is you increase one, you increase the other. But again, it's not really necessarily a doubling when we have other factors involved. So that could be, that's something you really want to pay attention to on, I guess, during your MCAT prep, because it's not that, it's not always as simple as saying when you double one, you double the other. What you do want to say is what you do to one, you typically do to the other when it's a direct correlation, when it's directly proportional like this. When they're directly proportional, you're gonna, when you increase one, you increase the other. Sometimes when you double one, you double the other. But when it's an inverse relationship, when we have something like A equals F over M, well, A and F are still directly proportional, but A and M now are inversely proportional. So if we held the force constant and double the mass, we'd have the acceleration. We would have that in. So a lot of different answers. There's no one simple answer. So the best thing you would want to do there is draw your picture, but also remember your equations too, and write the equation out. and then pick some numbers. Put numbers in, so you can actually just solve a problem to see what you get for your answer. So we're still looking at section 6.2, strings and springs, but now we're going to look at a spring, and the spring is always governed by Hooke's law. So Hooke's law is this equation right here, and it's always in the x direction. So we have a new equation, but notice how that looks like F equals ma. It just has a negative sign in it. For magnitude only, you drop the negative sign. But what Hooke's law is it's a statement for springs that says that a force is proportional or directly proportional to the amount the spring is stretched or compressed. And that the amount that the string is stretched or compressed, that's what the letter K is. K is called your spring constant, also called your force constant, and the units are newtons per meter. And it's a measure of how much your spring can be, again, stretched or compressed. The higher the number, the harder it is to stretch or compress it. And but more important than that, but we'll get back to that, but we still want to talk about this negative sign here. So the negative sign does not mean force is always in the negative direction, and we'll see why coming up. So we'll look at that pictorially here. So we start out over here with our letter A in our first picture, and it's we have no extension and no force, nothing going on yet. So then we come down here and we grab that hook, or we grab the little handle, and we start extending it. We're pulling it. We're pulling. We're taking the force, and you can tell by the spring that we're pulling it. We're stretching that spring, so we're pulling the applied force is in this direction here. So this is F applied, but the spring exerts its own force on the block. So the spring is resisting the effort you're doing right here. So you're pulling in one direction, but the spring is trying to fight you, and the spring is pulling in the opposite direction. So you continue, so you pull it and you go a delta x, you extend the spring by a distance x. But then you double that distance, and you see here where you double that force. And here we have our direct relationship, directly proportional. So when you double this one, you double this one. And K is a constant. So you can leave K off. You can actually just leave K off. And you have your force equals some constant times X. So when you double the force, you double X right here. And then similarly, when you come over to this picture, column B, once again, we start out with no force, and X is right at the 0 position marker. So then here now, when you want to go, you give it a positive displacement. You end up with a force pulling it back. But then when you actually do the opposite now, when you compress it, you now have a negative X. It's now on the negative side, and but now here you have a positive force. Here you have a little negative force going in one direction, and this is not. This force here is still positive, and so is this force here. It's just this one's it's still positive. We're seeing, as we can see from our coordinate system here. So the applied force is still positive, but the spring force back here is now positive. We have a negative displacement, but we have a positive force here. And this force also is negative. It's counterbalancing. This force is negative here because it's going in the opposite direction of the applied force. And then here the applied force is this way, and you have your positive force here again, still in the opposite direction. So the spring force is opposite to the displacement from equilibrium. So it depends on what you're doing to the spring. If you're stretching it, you're going to have a negative force like you do right there. And if you're compressing it, you'll wind up with a positive force. So you have a negative displacement there, and a positive displacement here. So we have two springs with a force constant. Each spring has its own force constant. So two springs, each with its own force constant, K1 and K2, and they're connected in series, which just means one's hanging from the other. And then we put a little mass attached to the spring on the bottom, and we want to know the amount of stretch that occurs with this amount of stretch that occurs when you put that little block on it. So we start out with our Hooke's law equation, negative kx, and then but here we're going to actually, since we clearly have one direction of motion. So because we have that, we're going to define down as positive. So we still have two springs, and what we want to do now is take this equation here and write it in terms of the two springs, because each one of them has their own k value. So because we went and defined down as positive, this negative sign starts out as positive now. So we can take Hooke's law and write it twice. Once for spring 1 and the other one for spring 2. But notice that the x's, we still use x1 for in both of those equations. So that's because these are going to act like a system. They're both going to contribute. They're both going to get stretched when you put this mass on, and it's going to result in one displacement of that block. So we're looking at what is the amount of the stretch as measured by the position of the block. And it's going from midpoint of the block to midpoint. So it's really this that displacement of the block. So when we look at it that way, what we can do now is so actually before we go on with our equation there, I wanted to get back to this picture here. So so we can say that this is x1 right there, and then this is x2 down here. So we can say that x1 starts at the origin because it's at rest. So the whole thing is at rest, and then we stretch it. So our origin will be right at x1, and then we get to x2. We get down to x2 once we stretched it out. But we still don't really want to change anything in this equation here, because we're looking for the total stretch. We're just looking for a delta right there, or one value. So we can go ahead and pull that x value out, and we can go ahead and write f equals x times k1 plus k2, and then we know that f equals ma. So we can combine the f equals ma and this equation right here, and we can see that we can just go ahead and add the ma down here, and we can see that this is our f, and it's equal to ma, and so now that we have it in this form here, we can go ahead and solve for x. So when we go ahead and solve for x, we're going to take this over here, and remember on this side we have ma. That's what this is right here. And then we're isolating x, so we're going to take that part and divide both sides by it. So we wind up with the equation right here. And we could actually go ahead and separate these out. And because we both know that they both have the same units here. So now that we have it here like this, we can go ahead and put our numbers in. But we actually want to keep these instead of keeping this as one equation, we want to go ahead and separate them out. So we want to separate them out here, and then go ahead and put in our spring constants. And we'll get to why. So the units are the same. So the units are both newtons per meter or Newton meter. So, but we don't want to go ahead and add them together, even though the unit analysis or units are the same. We don't want to add them together. We want to keep them separate here and go ahead in and plug our numbers in. So our x equals the mass the mass of 0.90 kilograms times our 9.81 meters per second squared divided by the first spring constant, 150 Newton meters. And then we get the same thing over here for the mass times our acceleration divided by the other spring constant. And then, so now that we have it this way, we can eliminate a lot of our units here, and we wind up with our value of x, or our calculation x equals 0.059 meters plus this 0 plus 0.035 meters, and for a value of x that actually equals x equals 0.094 meters. And the reason, so back to why we want to keep these separate like that, even though they're the same units. The reason we're keeping them separate is because K is a measure of the tightness or tautness of that spring. How difficult or how stiff is that spring? So when you think of your car, you want the springs in your car or the suspension system, you want that to be tight, because when you go over a speed bump, you don't want to keep bouncing. You want the car to snap right back into a stable situation. So, or same thing with if you hit a pothole, you don't want to start bouncing. So you want your springs to be tight enough to avoid balance, but you don't want it to be so rigid that if you hit a speed bump and instead of gliding over it, it felt more like you hit a brick wall. It's a little too jarring at that point. But you don't want them that stiff either. So you want them somewhere in between. But the point here is that you have two different springs, and each spring has its own value of tightness. So when we look at the two values, 150 Newton meters and 250 Newton meters, that's a big difference between them. It's 100 Newton meters separation. So we cannot conclude and should not conclude that putting the springs in series means that they both contribute equally to this displacement here. They do not. The looser spring, the 150, is actually going to give you a little bit more of a stretch. What we see right there, it's a little bit looser of a spring than the one we have there. So K1 gives us a little bit more, or contributes a little more to the determination of X, and so that's a good thing that we want to make sure we keep separate. When we do problems like this, is to recognize what K is. And again, K is a measure of the tightness of that spring. So there are two separate objects or two separate items that we're going to analyze, and we're going to analyze them both separately. So translational equilibrium is our next topic, and it refers to, or translational, the formal definition, is the process of moving something from one place to another. So that's what we did in kinematics, or that's what we are doing in kinematics. So last chapters 1 to 4, we identified our coordinate system, and we put our first position here and our final position, initial and final, and we moved from one place to another. Same thing with anything that was in the y direction. We started out the origin, we moved from one place to another. And even when we had an angle, we moved if this was our displacement right there, we moved in a combination of the x and the y direction. So kinematics is all about translational motion. Equilibrium is what keeps things suspended. So a really good problem to look at in the text is the one with the clothesline. And it's the one here where you have a bag of clothespins hanging there. So you have the two poles, and and then the clothesline, the bag is hanging there, but the bag doesn't, the bag's not moving back and forth. It's just literally hanging in the center. So it's hanging in equilibrium, and we could say that that's our zero right there, and positive to the right, negative to the left. And the bag just hangs right from that cable. And of course you have a tension in it, a tension here and a tension here. So when an object's in translational equilibrium, the net force is 0. So that's a really key thing. That's a very key concept, and here it is mathematically. So when a force, when something's in equilibrium, the net force, and again, your net force is this one here. Net force is the sum of all your forces. That's your net. And so your net force is going to be 0, and consequently your acceleration is 0. So you just have a mass there, and that's what we have here. The clothespin bag is a mass just hanging right from the line, and there's no acceleration. It's not moving. There's no acceleration. There's no velocity. Nothing at all. So it's just hanging there. So there's no acceleration, and consequently there's no force on it either. So the tension in this direction and the tension in this direction are equal and opposite. So because they're equal and opposite, you got limbo. Just like if you were arm wrestling with each other. If two people are arm wrestling and you both are applying the same force, nobody's moving to the left or right, and you're just stuck right at equilibrium, right at the middle. And again, that's what you have here too. So so again, when an object is in translational equilibrium, net force, which is the sum of all your forces, is 0. And that's the same as saying the acceleration is 0 because of these Newton's equation here. So here's our string and cable and application of equilibrium. So we did strings and springs, and then we went into equilibrium, and now we're combining them. So we have this string or rope, so right here, and then we're keeping this leg in equilibrium. We have, let's just say it's a broken bone, and so we have a break in the bone right there, and you don't want the bone to heal like that. You don't want this mass. You don't want them to sit on top of each other. You want it to be a nice clean. You want these two pieces of bone to come together and knit together very neatly without causing any overlap there, without the bone overlapping each other. So, or worse yet, if we looked at it from a top point, you don't want if this is the bottom bone, you don't want the top bone like off to the side either. You want you want a nice clean healing process there. So we're going to put just enough tension on the leg, and or just enough tension in these cables that consequently puts enough tension in the leg by pulling it right here, just at the right spot. So you can see here that we have our right triangle again right here, and our right triangle here, and then we see these equal and opposite forces T1 and T2, and then we see the angle. We're given the angles that it's pulling as well. So that traction device has 3 pulleys, and it's applied to a broken leg, and the middle pulley is attached to the sole of the foot, and that's the one that's putting all the tension on the foot, on the leg, to make sure that the bone just maintains its position, its set position. And then a mass M at the bottom supplies the tension in the rope, and we want to find out what that value of mass, what the mass is, in order to put the force exerted on the sole. We want that to be 165 newtons. So if you were the orthopedist, somehow or other you would come up with needing 165 newtons applied to that foot to keep the bone from overlapping, or just to make sure it heals properly. So you know what the force is that you want on the foot, and you have to find the mass that it's going to give you that's going to give you that force. So here's our drawing. I just put that on pause a little bit to draw them, and so I redrew the 2 triangles from the earlier picture, and so here's the original 2 triangles, and then these are the equal triangles on the side. So we're just showing that this side right here is t sine theta for both of them. And then this side right here and this side right here, each of those is t cosine 40. And so we want to analyze each triangle separately. So the tension is what we're looking for. We want is to find the mass m if the force exerted on the sole is to be 165. So that the 165, that's the tension right there. So we know what the tension is, but we don't know what the mass is. So that's what we want to find. So the tension on the upper triangle, the tension on the upper part, so we're going to put T1. So we'll make this T1 and this T2. So the tension on the upper part is in the, remember that tension's a vector. So it's this overall tension right there is the sum of the tension in the x direction and plus the tension in the y direction. So our tension in the x direction is this t cosine 40 degrees, and that'll be in our x direction. And then our t sine 40 in the y direction. And then our T2, we do the same thing there. T2 is also, we are in the x direction, we have our t cosine 40. And then now we're going to add our this t sine. So what we did with our coordinate system is we made this the positive x direction and that positive y, and then this one negative y. So this t sine theta right here is in the negative direction. So we're going to put a negative t sine 40 degrees, and that's in the y direction there. We'll put that in the y direction. So and then we also know, or we also want to remember that the tension in the rope. So what I didn't actually draw down here is let me draw the foot, and you have. So you have your 3 pulleys right here, and then here's your mass right there. So that mass has a weight. The mass there's a weight here too, and that's also in the y direction. The tension in the rope is so we want to put that equation up here too. The tension in the rope is the weight, and it equals weight equals mg. So the top and the bottom pulleys are exerting the force on the string that's pulling the sole straight forward. So we want to resolve the tensions into their components. So let's go back up to our equations up here, our T1 and T2, and we'll keep our we'll separate them out into just their components here. So we get T cosine 40 in the x direction and T2 in the x direction. And then T1 in the y direction is our t sine 40. And then T2 in the y direction is the negative t sine 40. So we know that tension, we know when we want to solve this, it's going to be our tension, summation of our tensions, equals MA, or however we want to proceed with that. But let's just let's go a little slower here for that before we get to that part. So we just want to remember that our tensions are sums. So so right here, because these are equal and opposite, that sums to 0. But then over here we get 2t. We get 2t cosine 40. So that makes it a lot simpler to solve. So the force in the y direction is 0. And that would make sense when you look at this foot. The patient's laying in bed and the foot is in the x direction. The last thing you want is it moving up and down. So you want nothing in the y direction. And it worked out that our pulley system right here was set up correctly. And it worked out that the tensions in the y were equal and opposite, so they canceled each other out. You need them, you have to have the tension there, but you want them to cancel out. You want the sum of the two tensions in the y direction to be 0. if this one down here was wobbling, or maybe rotating it this way, that would be bad. And again, you don't want it bouncing up and down either. So you should have that. It's good that that came to 0. So that indicates that we set up the pulleys correctly. So so now we just want the tension just in that X direction. And we said here, when we come back up here, normally we would say T equals MA, or F equals MA. And we're given that right there. We're given it as this 165. So we found our summation of our T's right here, and we can set that equal to the 165 newtons. And we can solve for T now. We can solve for T by dividing through by the 2 cosine 40. So we wind up with T equals 165 newtons divided by the 2 cosine 40, and that gives us 108 newtons. But we still didn't find the mass yet. We want to know what that mass is. And so here we're gonna come back here. So we know that we have this tension now. We have a total force up here of 165, and again, that's the combination in the y and the x directions here, the overall force. But when we put it in a pulley like this, we change direction, and that also means it kind of dampens a little bit of the force, and we see it being reduced a little bit here by the x direction. And so now when we want to go solve for the mass, we want to take our tension and set it equal to the weight, and set that equal to the weight, and then solve for m, where we divide through by g. So we have our tension divided by g, and that's going to be 108 newtons divided by our 9.81 meters per second squared, and that gives us a mass equal to 11.08 kilograms. So so the force on the sole of the foot is 165, but the tension required in the overall cabling system to give you 165 newtons of force, the tension has to be 108. So what'll give us that 108, and consequently the 165, is a mass equal to 11 kilograms. So when you add 3 pulleys, you get if you add the 3 pulleys in there, you're able to increase. You're able to basically translate your tension into, or parlay your tension into a force that's greater than the tension, and that's what we did here. We had this tiny little 11 kilogram mass that created a tension of 108, which created a pulling force or pulling tension on the foot of 165 newtons. So it would have taken a lot bigger of a weight if we took this foot right here, and so if we took this foot right here, and if we just pulled straight this way, like say we wanted to put some hook on the wall. So maybe this is the wall with a hook, and we wanted to tie the rope this way and just keep pulling the foot straight out. Well, we would have had to have a much higher tension on there, or a way to adjust, kind of like the way braces are adjusted on teeth, a way to adjust this or set it at that 165 newtons. So that's a contraption, obviously, that most hospital rooms would not be able to accommodate. But something as simple as pulleys and strings and tiny little weights, it's a very affordable solution to setting a leg, or to putting something in traction. I'm sorry, I don't think I forgot to turn that back on. So what I drew up here is the 3 boxes from chapter 2, and so we're talking about connected objects here. And I said chapter 2, I mean chapter 5. So chapter 5, we solved the problem where we had 3 boxes in contact. They were physically in contact with each other, and one force was applied right here, and they all moved with the same acceleration. So if you're having trouble visualizing why they all move with the same acceleration, take 3 objects. It could be 3 boxes, or you could take 3 cell phones or 3 books, Just pick 3 objects, and they don't even have to be the same size, and put them in physical contact with each other. Don't stack them. Don't stack them on top of each other. Set it up like the 3 boxes here that we saw in chapter 5. So when you put the 3 items in contact with each other, and then you apply that one force, they're all going to move with the same acceleration. It's if one actually, if say this one right there moved at a faster acceleration, then it's moving faster than these 2 boxes, and consequently it would no longer be in contact with these boxes. If this one sped up, it wouldn't be in contact anymore with the other ones. So as long as they're staying in contact with each other, they're moving at the same rate. So that's a little different than than shooting pool. So you hit one ball with the cue stick, and that ball hits another ball, but both balls go off in different directions. They don't stay connected. So one might have been at rest, and the ball that you hit with the cue stick, you gave that ball an acceleration, and it accelerated over to the other ball and hit it, and started that. So that when it hit it, it exerted a force on that mass that gave it an acceleration. So you already put the cue ball in acceleration or in motion, and then it in turn put the other ball in motion. But as you can see, when you shoot pool, the 2 objects don't stick together. The 2 balls do not stick together. They just go off in different directions at their own acceleration rate, or at their own rate of acceleration. But when you have objects together that are connected here, they don't have to be glued together. They just have to be next to each other, or physical contact that's very loose, like just putting 3 cell phones on the table. And when you push them, they all act as a system. So this one right here, this entire thing is one system. So they're all going to act together and move together and have the same acceleration. And similarly down here, these boxes with the string between them is one system as well. So the whole system is going to move with the same acceleration. So one thing though, even though the whole system is going to move with the same acceleration, it often gets a lot easier that instead of treating it like one system, it turns out to be a little easier mathematically if we actually treated them as 2 separate systems, and we put the dividing line, right down the middle, where that breaking point would be, with the 2 tensions pulling in opposite directions. So now we could set them aside here, and then we see that the horizontal components are what contributes to the motion. And this one, this T is in the negative direction, and this one's in the positive direction. So that's why it's easier to break them apart, to separate them out, because this T again is negative, and this one's positive. So it just gets a little easier to set up you can put the coordinate system right there as 0, and then 0 right here. And on this side, everything's positive, but then over here you have a positive and a negative. So circular motion is the next really big topic, very, very critical topic. And we sort of were seeing that in the last or chapters 1 to 4, but we really keep that separate. And it's also separate than rotational motion, not the same thing. So circular motion and rotational motion, they're both going around a circle. They're both moving in a circular pattern that we're showing right here. It's just that with circular motion, there's no fixed axis. It looks like there is. It looks like a rigid axis right here, but it actually is not. With rotational motion like a Ferris wheel, that definitely has a fixed axis. So a Ferris wheel, it would be the fixed axis is at the apex of the triangle, and then the wheel itself is what's spinning, and it's spinning about that axis. But circular motion, this axis doesn't have to be fixed, and we'll see that in this picture over, or the one coming up. I thought I had it earlier. I'm not sure where I have that now, but it's the one where the guy's swinging the cork overhead. So if you think of if you take a string and you tie an object on the end of the string, a stone or whatever, and you swing that overhead, the axis of rotation could be your wrist, it could be your shoulder, it could be your hand, and all of those flex and change. So if you're swinging something overhead, your shoulder is going to be rotating, but your arm is going to bend at the elbow, and even if you try to keep it straight, you can still move your hand, bending that. So there's no rigid, fixed axis of rotation. Even your shoulder, even with it rotating as it's going around, you can be wobbling back and forth, so that moves your shoulder around and everything else too. So circular motion is motion in a circle, but not about a fixed axis. So Newton's law is second law. It still applies to circular motion. The second law is that if there's no force acting on the object, it's going to move with constant speed in a constant direction. So an applied force or some force, external force or net force, is required to change that speed and direction. So again, if you think of the projectile motion, if you have the football right there or the soccer ball, and the guy comes up and kicks it, it goes in a parabolic path. So gravity is acting downward on it. Gravity is pulling it in that parabolic path, pulling it down there. Well, if gravity did not exist, if there was no gravity, it would move at constant speed and with constant direction. It would just go off that way. So here, it's in this picture here, that's changing direction. So think of that roller coaster graph that we had where we said acceleration and force, when they're in opposite directions, it's slowing down. When they're in the same direction, it's speeding up. And when they're perpendicular, they're changing direction. And I think perpendicular was written more like in this direction and one right there. So that means they're changing direction. So if we think of that graph again, let me erase the lines on there so we can visualize that a little better. Looking at that graph again, where we had the arrows, this is the first part of circular motion. We can take that and complete the circle, and that's what we get right up here. So we get circular motion, and we have and that's right around that circle is there is our where velocity and acceleration are in different directions. They're perpendicular to each other, and that when they're perpendicular, they're changing. So let's look at what we got over here. I can erase all the way back. So basically what we have here is we have this velocity here, and then we're going to see that we have a acceleration right there. Here's our velocity and here's our acceleration. And all around, right up here is a velocity, and here's an acceleration. So all the way around that, this triangle just moves around that circle, and it's constantly changing direction. It may not be changing speed, but it's definitely changing direction. So the object moving in a circle has to have a force that's acting on it. Otherwise, it would move in a straight line. And that moving in a straight line, that's what we see right here. And then same right here, and that straight line is a tangent. So if you're swinging an object overhead and you just keep swinging it in a circle, you're forming a circle or swinging it overhead in a circle, and you let go of the rope, it's going to fly off on that tangent. It's not going to continue making a halo over your head. You're swinging it overhead in a circle as though it's a halo. But once you let go, it does not continue swirling around. You let go, and it flies off on a tangent, goes off on a straight line. So to make the object move in a circle with a constant speed, the direction of the force on the object is towards the center. So and we know that from this picture. We just put acceleration towards the center. So and then we know from our concept with F equals ma that the force and the acceleration are always in the same direction. So that force and that acceleration are center seeking, and that's called centripetal acceleration. And so if we look a little bit more, here's our centripetal acceleration right here. So the object is also accelerating towards the center of the circle. It's accelerating. Around the circle. It's accelerating around the circle here. So that could be a combination of our translational, and it's accelerating towards the center. So this is our centripetal acceleration right there, a center directed or centripetal. So the object, the constant speed means acceleration 0. And so actually we're not, if we have constant speed. If we have constant speed, we don't have acceleration here. But it's possible when you're swinging that object over your head, it's possible for you to not keep it at a constant acceleration. It's possible for you to keep speeding it up and slowing it down and speeding it up. So in that case, it would not be constant speed. But if we assume here in this circular motion that it's constant speed, then that means the acceleration is 0. And that would be this acceleration up here. So the acceleration is produced when the magnitude of the velocity, which is speed, or the direction of the velocity changes. And we're seeing this direction change all around the circle. So in circular motion, direction is always changing, but the magnitude of the velocity remains the same. So there's our assumption that velocity is constant speed, and consequently 0 acceleration. So our equation for circular motion, it's still velocity velocity over position now instead of velocity over time or change in velocity. Instead, when an object is moving in a circle of radius r, we have to take that radius into consideration. So the centripetal acceleration, a sub cp, right here, is equal to v squared over r. And the force, a force associated with this centripetal acceleration. So a force associated with the centripetal acceleration, this is the cause. So it's the force that's causing, that's the word causing, sorry, causing the a sub cp. So there's a force that's causing that acceleration. And that force is being applied to the object in order to give it the circular motion and consequently the centripetal acceleration. So for an object of mass m, the net force acting on it must have a magnitude given by this formula down here, and it must always be directed towards the center. So just the key to remember there is, go back to this slide here, centripetal acceleration is center directed or center seeking. So it's always pointing, it's going to always point towards the center, which is our origin in the circle. And then, and of course, our centripetal acceleration force is also equal to ma. So we still have our Newton's law of F equals ma, and then A equals the v squared over r, and we substitute that in. So I think when I had the friction lecture, when I was going through that, I said that the friction force is the only one that's lowercase. That's obviously now a mistake. I forgot about centripetal force. So centripetal force is also lowercase. And then the centripetal acceleration would have CP after it, and the same with centripetal force. Just like static friction and kinetic friction have their subletters. Same thing with centripetal force. It too has that subscript, C, and the subscript here is CP for centripetal. So here's the picture of the guy swinging the ball over his head. So circular motion, we can create that by putting this ball on a string, and we see the tension directed towards each other again. The tension he's applying, and then he's applying the tension to this end of the cord, and the ball is applying tension to that end of the cord. So the force might be provided by the tension in the string. Sometimes it could be provided by the normal force or friction. So that centripetal force can be created by a variety of different things. It's not necessarily a person that's creating that centripetal force. It could be the normal force that's causing centripetal acceleration. It could be friction, and we see that here in the car, where the car going around the bend, the force of the weight of the car it keeps it down on the ground. And then we have that friction right here. I just wrote over that, but see if you see right here, you can see right there that F sub S is static friction. So static friction, along with the normal and the weight, is what keeps that car on the road. And notice that this car's not embanked, so it's different when you get an embankment. And but when you get a road that's not embanked, you have 3 different forces come into play to keep that car on the road. And of course, we know that cars skid off. We know that cars, when they're going around the bend like that, they often don't make it and they skid into the ditch. And that's because the centripetal acceleration that's going this way, and that centripetal or the static friction. Static friction has a threshold. And remember that equation or that relationship? It's here's the max right here, and then greater than equal to 0. So some maximum gets it moving, but then there's another maximum upper limit that's so great that when it's exceeded, friction's not going to do anything anymore. You overcame that force, and if you do that, if you overcome it, so like speeding, if you're going too fast, you won't be able to take the bend in the car and the bend in the road, and the car will fly off of the curve. You won't make it around. So you can exceed that limit, and you can exceed the limit or the max, and then lose control of the car. So again, going around a bend that's not an embankment, we have static friction, the normal force, and the weight of the car creating that centripetal force. And then here's our embankment. So one thing we want to know, or one thing that we want to, we in the last slide, we saw the track that was not embanked, and here we see a track that is banked. And then we saw in the last slide the circle over the guy's head. But the circle does not have to be a complete circle, just like we saw on that picture when we were talking about V and A in opposite directions and perpendicular and same direction. Well, that's a half of a circle right there. And here's the full circle here too. So in this case, we just have a car going over part of the circle, and that's fine. There's nothing wrong with that. And so that's still considered circular motion. The car right here is operating in circular motion when it goes over the bump in the road. And then when we come up to this racetrack right here, here's the one of the few examples that we do where the normal is literally not equal and opposite to the weight. So when we're going around this bank, we start out with we have our x and y coordinates right here, and the normal force is perpendicular to the surface on which the object resides. So the object is the car and the surface is the road. So this normal force has to be perpendicular. And we see the perpendicularity right here of the road, and then the normal force perpendicular to it. So now when we solve a problem like that, we have to treat n as literally the way we treated all our other vectors, where n is going to equal the sum of its components. So we'd have to break n into its x and y components, and then we got to do the same with w as well, with the weight, break that into its x and y components. So here we're going to solve this problem here. So a car is going around a curve on a road, and so as the car is going around a road, though, we can tell right up here that we have. We can tell right up here that we have a couple of right triangles. But let's take a look at that in a little bit more detail, though, on how to best set this up. So so we can think of our x and y system right here, our x coordinate, and then our y coordinate, and then we have n coming out this way at an angle of theta. So there's our first triangle, and this will be n sine theta because it's the opposite, and then this will be n cosine theta right here, and then we have we have w. We have our w right here, and that's actually right in line with the y-axis. So we'll make that a little thicker, and we'll call that w. So actually w. I'm sorry, I said w. We had to break into its components, but that was. If I drew the n vector all the way down, then we see it making an angle with the n vector right there. So so we want to, what's our problem asking us here? So the road's slick, but the car is going to stay on the road without any friction between the tires and the road when the speed is 19.8 meters per second squared. So we want to know what this radius is. We want to calculate the radius of that circle. So so the radius is in this x-axis. It's in this x-axis right here. So we want to sum. We want to go ahead and sum all of our forces in the x direction. So our force in the x direction is this one right up here. It's that n sine theta. And then that looks like everything, n sine theta, because w is entirely in the y direction. So that's our force, or F sub x, the force in the x direction, n sine theta, and force equals ma. So if it's a little easier for you, see the way I wrote that right here with the I wrote it with an equal sign there. If it's easier for you, maybe another way is to write it this way. So you get rid of those equating signs. So that just indicates that our F sub x is this right here. It's our forces. It's the summation of all of our forces, and we only had one force in this case here, or in the x direction. So we put our force here, and we set it to ma based on Newton's law. And then we know that we know that A sub Cp equals V squared over R. So that's where the R comes in. That's where, and I should put Cp right there. So we can now say, or we can substitute that in. So let's come back over here, and we'll write our equation over here. N sine theta is going to equal ma, but a equals v squared over r. So now we can solve for r. R is in the denominator down here, so we're going to bring it up here to the numerator, cross multiply. So we get r, but we want this component to come down there. So we're just rearranging our equation here. We're going to keep our mv squared at the top, and now we get this n sine theta from over here, from this part right there, that moves over to the other side of the equation, or changes places, like r swaps with n sine theta. So this equation, we want to set this aside for a minute. So that's our equation 1, and we don't really have everything yet to plug in there. We know that the angle is 21.5, and we know that the speed is 19.8. But we don't know n, and we don't know m or n. So n is still unknown, and we want to find, and we'll find the velocity and solve for f sub y. So we I'm sorry, we have the speed. We actually do know the speed. So we have v squared here, and so that's our f sub x, but we'll need our v or our f sub y in order to solve for some other parameters like that value of n, or see what we can get here. So let's go ahead and set up our f sub y equations. So our summation of the forces in the y direction. So in the y direction, that's going to be our n cosine theta. And then in the y direction also is this weight right here. So that's in the negative x direction, and that's okay. Even if we put a plus sign there, we would then put a negative in for the g. But keep the negative, because that's what you've been doing. It's in the negative y direction, so you put that negative in there. So this is our force, or sum of our forces. We have the one force, see right here, our sum of our forces in the y direction, one force and the second force. We have two of them. Two forces we're adding here, and force equals ma. So we're going to substitute that there. So here's where this equation or actually no, I'm sorry, we don't need the equation 1 yet. We want to go ahead and take a look at this equation 2 a little longer here. So what we can say is that this acceleration over there is 0. And why do we want to say that a is 0? That's because in this equation we're working in the y direction. So a is just in the x direction. It's in a track. Remember, it's going around the track, which is all in the x direction. There's no corresponding value of acceleration in the y direction. So this cancels out. It goes to 0. So now that helped us a lot. Now we can solve this equation for n. So we'll keep our n over here. Move this mg to the other side of the equation and divide by that cosine theta. So we wind up with mg divided by cosine theta. And so now we can take that value and we can plug it in to equation 1. And then here's where some of our math some of our geometry relationships come into play. So let me see if I have any room on, not a lot on that chart there. Actually, yeah, I think I'll try to keep it here so you can still see all the math there. So so if we go up to our equation for r, and let me change my ink color here. So so we want to go up to we want to go ahead. We want to take this value of n right here and plug it into our value of r. So r equals mv squared divided by n, and n is this equation right here. So we get mg divided by cosine of theta, and then our sine theta right here. So we take so we keep that sine theta right there. So that's what we did. We have our r equals mv squared divided by n, which equals this value here times sine of theta. So what we can do now is look at our geometry here. Let me erase this cosine. So if we look at our geometry right here, we have sine over cosine. Well, sine over cosine is tangent. And what we can do though, before we even plug that in, let's go ahead and we don't want to change that yet. Sine over cosine is tangent. But what we really want to do is really, we still have this cosine down here that's underneath the mg. So let's simplify. Let's rearrange our equation a little better. We get mv squared, and this cosine over here is in the denominator, and when we inverse multiply, it brings the cosine to the top. So that leaves us with mg sine of theta down below, and cosine over sine. Now we saw here sine over cosine is tangent. Well, cosine over sine is inverse tangent. And but look also right there, we can cross that mass out. So we just got rid of an unknown. We just crossed that out. So r is going to equal our v squared divided by g, and this value right there, cosine over sine, is inverse tangent. But now what we could do is inverse tangent also is 1 over tangent. So that's what goes here. When that cosine, we put our tangent down here, and then we can go ahead now and actually plug values in. So r equals v squared, and v is 19.8 and meters per second, and all that's squared, divided by our 9.81 times our tangent of 21.5. So R ends up equaling 101 meters. So I think in some of the homework you have a problem where you're on a road that's not banked. But I think I'll try and solve that problem and put that presentation up too. So of course, if you have any questions, please do reach out, and we can go through. We can set up a little conference or whatever you need to get answers to you. So thank you, and I'll see you at Chapter 7.